Dear all, welcome to this section of the course of Numerical Methods for ActiveMatter. In this section, I will talk about numerical techniques on simulating random walk, Brownian motion, and active Brownian motion, and some characteristic behavior that is arising from these kind of motions. Some of them, as can be seen from the videos that are playing on the side. My name is Aykut Argun, and I'm from the University of Gothenburg. Hopefully, you will enjoy this lecture. And let's get started. This is an outline of my talk, so we will begin with an introduction to random walk, and we are going to investigate some of its characteristics, and then we will move on to diffusion and Brownian motion, and then we will discover some numerical techniques simulating optical trapping of Brownian particles and analyzing some of the properties of the trajectories, and then we will move on to active Brownian motion and see how we simulate that. And then we are going to observe some clustering behaviors of active particles using the numerical methods that we have learned. And at the end, I will introduce some problems that you can move, work further on to develop your learnings in this course. So without further ado, let's begin with the introduction of random walks. Let's begin with understanding random walk in one dimension. So, the simplest form of random walk can be considered as flipping a coin, and then we take a step to the right if we get heads and take a step to the left if we get tails. So the difference equation of such a walk can be given as this equation, where W flip can either be -1 or +1. So here is a sample trajectory that you see generated from this kind of random walk. So at each time step, particle can either go to the left or go to the right with equal probability. One of the important problems that arise with such systems is called stochasticity, which means that each realization will yield different results. For example, here you see that 3 trajectories that are generated from the same random walk algorithm, and they all end up in different positions. So it's very difficult to predict what is going to happen at the end because it will be different for each realization of the random walk experiment. However, we can still look at some statistical properties of these trajectories if we can make an ensemble average to check what are the average characteristics of these different trajectories. The first one that comes to our minds is the average. What happens to the average of x if we go n steps? In this case, since the probabilities of going to the right and going to the left are totally symmetric, the average will always be 0 for the entire ensemble. So this obviously doesn't give us a very good opinion, but we can also have a look at what is going to be the square of x after n steps. So this is also referred to most of the time in literature as mean squared displacement. So what happens, what is the average squared displacement that I will have after n steps of random walk with a flipping coin? This is an important question, and let's have a deeper look into that. We simply start by guessing what would be the x1 square after one step. In this case, it's very simple. I will go to the left with a 50% probability, and I go to the right with 50% probability. So my square displacement will be 1 in each case. So this will give me mean square displacement 1. So MSD1 will be equal to 1. What happens after 2 steps is that I can go 2 steps to the left, or I can go 1 step to the left, 1 step to the right, and I can go 1 step to the right and then 1 step back to the left, and then I can go 2 steps to the right. This gives these kind of probabilities, and my mean square displacement, if you do the math, will be equal to 2. And you can continue do the same math for 3 steps, and you will compute at the end that your actually mean square displacement will be 3. In fact, it's not very difficult to show that for this kind of a random walk, mean square displacement for I plus 1 steps will be mean square displacement for ith step plus 1. So here in this example, we actually see that the mean square displacement increases linearly with time with such a random walk. Let's begin by making a simple exercise with random walks. which is simulating random walks with different random number distributions. However, they will all have some important characteristics, which is first, they will not have a non-zero mean, which means the particle average position will stay the same. Secondly, they will have the same kind of mean square displacement change for each step. So here is the exercise. So we are going to have three different probability distributions for our random walks. The first one is the one that we saw in the last slide, that is a flip coin. So we go to the left with 50% probability with +1, or we go in the other direction with 50% probability. And the second distribution of the random walk steps is the Gaussian distribution. And the third one is given here. So this is an asymmetric distribution, and this creates still gives an average displacement that is 0 and average square displacement that is 1. So these are the characteristics that all these three random walk step distributions share. From these, we are going to first create sample trajectories and show that they all look very similar if we have displaced large number of steps. And then we are going to compare where they end up at in the coordinate in x after 10,000 steps, and we are going to see that their distribution actually look identical to each other. So this exercise now you're going to supposed to work on and prove for yourselves and observe that this actually is true. I recommend that now you pause the video and then go work on this exercise until you're done, and then move on with the rest of the lecture. Let's move on to diffusion and Brownian motion section. In this case, first we are going to look at how to simulate a random walk with rescaling the time difference of the simulation delta t, and also we are going to see how to simulate diffusion with real units, which brings us to Brownian motion. We start with a very important concept, that is programming diffusion with different time scales. So a simple diffusion equation can be represented with a very similar equation to a random walk, which is the time derivative of x will be equal to w of t, where w of t represents the noise, which depends on time that is driving our particle's position. However, if we want to simulate this, we need to convert it into a difference equation. In this case, it can take a form that can be expressed as xi plus 1 is equal xi plus wi times delta t, where delta t is the time step of our simulation and wi is the noise term, the random number that we generate in each time step. So it's not difficult to see that the square displacement for each step for this kind of a random walk will be the square of this term, which will yield in n steps and mean square displacement that is n times sigma squared w of delta t square. In order to see the mean square displacement as a function of t, we can make the substitution n times delta t is equal to t, so that we, instead of as a function of a number of time steps, we can try to see the mean square displacement of x as a function of time. So we can substitute this expression into our initial expression, and then we end up with this equation that the mean square displacement at time t will be given as sigma squared w times delta t times t. So obviously here we encounter an expression that is kind of dependent on delta t, which should not be the issue, because if we change the time step of our simulation, the characteristics of our motion should not depend on our time step. That is why we need to reweight our random numbers according to our time step, and we need to rescale them with proportional to 1 over square root of delta t. This gives us a similar kind of overall mean square displacement characteristics, even if we change delta t for our simulations. So here small wi refers to just a random number with variance 1 and mean 0. So you can generate this very easily with rand n in any kind of programming language. If we substitute this expression into the original equation that we had, we end up with this kind of difference equation for a diffusion of a particle. So xt plus delta t is equal to xt plus wi times square root of delta t. So this expression will hopefully give us results that will not depend on our time step choice delta t. And we are going to verify this in the next exercise. In this exercise, we are going to show that if we are going to use this kind of expression to simulate diffusion, we are going to observe that it doesn't matter what we choose as a time step delta t, we will end up in the very similar characteristics of trajectories, even for very largely different delta t values. So as an example, we are supposed to simulate a diffusion equation that is given here for delta t is equal to 0.01, 0.05, and 0.1. And of course, we want to simulate trajectories that are similarly long in time, that is 5 seconds for each system. And then we are gonna, of course, the number of steps will be very different for each one, because for the time step that is 0.01, the number of steps will be 500 total steps to reach 5 seconds. For the second one, the number of steps will be 100. And for the third one, the number of total steps will only be 50. However, if we plot a few trajectories, we will observe that they all look very similar in the same overall timescales. And also, if we just simulate a lot of them and take the average mean square displacement, we will observe that they look very similar to each other. So this shows that rescaling our noise term correctly according to our choice of delta t will give us consistent results even if we change our delta t term. Okay, now we have understood the very basics, we can move on with programming diffusion with physical parameters. So the initial diffusion equation that we simulated in the previous slides were represented as the time derivative of x was equal to some kind of noise term w that was changing over time. However, in real world, this random term acts on our real physical particles as forces, which creates a differential equation for particles motion, which is defined as, which is the Langevin equation that is given as this form. So here you see that we don't only depend on the first derivative of our position, but also the second derivative because our particles have inertia. And also you see some terms that are getting involved, which is the Boltzmann term kBt, because we are in a water environment and there is a temperature and we are coupled to a heat bath, and gamma here is the friction term. We can represent this expression as a difference equation and it will give us this kind of form of an equation. And here note that we also rescaled our random number similar to the exercise before, and we rescale it according to our choice of delta t. And here the solution of this difference equation can be given as this. So this is how we are going to simulate diffusion with real physical parameters for a microscopic particle. However, there is an important point that we need to take into account here. There is this term that is delta t, the ratio of delta t to this term that is m divided by gamma, which can be represented as the characteristic timescales of momentum relaxation of the particle. So these timescales are often very small in the order of nanoseconds, and if our choice of delta t is large enough, these there are lots of terms here in this equation that can be approximated to a much simpler expression. If we assume that our choice of delta t is much larger than the characteristic time tau, it's not difficult to see that this complicated difference equation will take a much simpler form that is shown here. This will give us a much easier possibility to simulate because it's much simpler in terms of expression and it's not in second order, it's only in first order. So we have two different equations. One is the initial solution to our Langevin equation, that is what we are going to call the inertial equation. And the other one is the equation approximation that we make when we assume that our time scales are much larger than the momentum relaxation time of the particle. And this equation is we are going to refer as non-inertial. And in this exercise, we are going to simulate our Brownian particles motion with both of these equations, and we are going to compare them. In this exercise, you can take gamma, the friction term, as 6 pi times the radius of the particles times 10 to power minus 3. And you can use the parameters that are given in this exercise box. And we are supposed to observe that for very short time scales, this non-inertial approximation is not giving us correct results. However, if our time scales are greater than this characteristic time tau, it will give identical results. And we will also see this in trajectories at short time scale, long time scale, and when we look at trajectories and mean square displacements at different time scales, we are going to verify this, as you can see in this figure. And I highly recommend you finish this exercise before moving on to the next section. Now that we have seen how to simulate a free Brownian particle, we can try to go ahead and simulate a Brownian particle that is confined in an environment. Arturashkin has shown that a microscopic particle can be trapped within the hotspot of a highly focused laser beam. In fact, he has received a Nobel Prize for his discovery. So in this animation, you see that a microscopic particle is placed in the center of a highly focusing laser beam, and due to the change of the momentum of the light beams that is refracted by the particle, there is a counteracting force acting on our particle, and this force is always pointing to a center of the focusing of the laser beam. So this creates an effective trapping on the particle, and actually it can be used to trap or manipulate microscopic particles. This method have been widely used to trap a lot of different particles, from biomolecules to microscopic cells, from artificial colloids to even single atoms or ions. In the next step, we are going to simulate a Brownian particle that is confined in an optical trap. In the case of free diffusion, this was our equation that was simulating our particle, whereas for the case of optically trapped particle, we are going to add a term for the confinement that will be represented by this minus kx. And this will give us a force that is very similar to a spring force that is recalling our particle back to the confinement center. Our choice of the time step delta t will very often be quite large for these systems, so we can actually assume that we are going to be in the non-inertial regime and make the viscous approximation like we did before, and the difference equation for an optically trapped Brownian particle will take a form that will be looking like this. Unlike a free Brownian particle that is represented as the blue line in this plot, an optically trapped particle will stay at confinement point and will only oscillate around this equilibrium position, as it can be seen from the red line in the plot. The next objective that we are going to have is going to be to simulate a Brownian particle that is optically trapped and analyze some of the characteristics of its trajectory. Some of the characteristics can be given as follows. The first one is the Boltzmann distribution. The particle will follow the probability distribution as predicted by the Boltzmann's law. Another important characteristics, that is the variance of the particles, will depend on our stiffness K, that is given as this formula. And a third important parameter that will be encoded in our trajectories of a Brownian particle that is optically trapped is the position autocorrelation function. We will go into the details of this autocorrelation in the next slide, but this can also be predicted. Here is the text of the exercise. So we are going to simulate a Brownian particle that is optically trapped in 2 dimensions, and the stiffness values for each dimension will be different. The stiffness along x will be stronger than the stiffness along y. In the first part, you are going to derive the 2D trajectory of the particle and plot it as it can be, as a sample can be shown in this figure A here. And then you're going to calculate the probability distributions for both X and Y and show that they actually follow Boltzmann distribution prediction that was given in the previous slide and also in the lecture notes. That can be shown in B here. And then you're going to compute the autocorrelation functions for X and Y and compare that to the theoretical prediction. The details of the autocorrelation function and how to calculate it numerically can be found in the lecture notes in detail. And the last part, you are going to simulate the particle of an optically trapped particle for 1D for various values of the stiffness, and then you are going to show that the variance of the particles is scaling with 1 over k. So as it can be seen from plot that is in D. Unlike a normal Brownian particle that is diffusing randomly around the liquid environment, an active Brownian particle will propel itself with a certain velocity v. This will change the equations of motions along x and y with an additional term that is represented by this propulsion. However, we also in this case have a third equation that is representing the particle's orientation because it gets relevant because of this propulsion. And this orientation of the particle is often changing over time randomly, just like the position with due to random collisions from the liquid molecules, and this is called rotational diffusion. And the important parameter about the rotational diffusion constant is that it's often scaling with 1 over r cubed, whereas the original diffusion constant, translational diffusion constant, is often scales by the temperature divided by the radius of the particle. So as the particle gets smaller, the rotational diffusion will get much larger than the translational diffusion. And here you see some sample trajectories of Brownian particles that is moving at a speed of 3 microns per second. In this next exercise, you are going to generate difference equations for the case of active Brownian motion and simulate active Brownian particles with different velocities and different translation and rotational diffusions and try to observe how the different trajectories look like. As a reference, you can see, you can have a look at this figure that is provided in the lecture notes as well. That is a plot for the 4 different Brownian particles that have different propulsion speeds, and as a result, their mean square displacements are monitored, and you see that they kind of have a super diffusive behavior for short time scales, whereas for the long time scales, they all kind of same kind of diffusive behavior. Once we have learned how to simulate a single active Brownian particle, we are going to next make a series of exercises that we observe how to make these active particles collectively moving in an environment together. In order to do this, we are going to simulate, instead of one, many active Brownian particles that are placed in the same environment, and we can have some kind of periodic boundary conditions in such a way that if a particle is disappearing from one side, it will enter the frame from the other side. And the first thing we're going to need to apply is what we call a volume extraction. So we know we have treated all the particles individually so far, but if they are placed in the same environment, they cannot overlap between each other. This can be solved by, at the end of each time step, we can just separate the particles that are overlapping by a certain amount that they kind of remove the overlap. The details of this overlap removal is written in the lecture notes, and in this example you're going to prepare such an example that active particles are swimming around with some translation and rotational diffusion, and they kind of once in a while get pushed by each other because they kind of encounter another swimmer, as it can be seen in this video. Once we succeed the simulations that are shown in the previous slide, we can move on with adding some more complicated properties to our simulation, such as a phoretic interaction. Phoretic interaction can be described by particles that attract each other with a force that is inversely proportional to the distance between them. If we involve this kind of phoretic interaction, the particle will tend to stick to each other and create clusters more often. And as it can be seen in this video, if the value of this phoretic interaction is negative, then the particles will push each other and they will tend to stay away from each other as much as possible. And as a last exercise, we are going to simulate active particles that have aligning interactions. In this case, the particles will tend to change their directions if there's a nearby particle in order to align themselves with that particle that is given analytically by this formula. And this will only take place if the distance between the particles is smaller than a certain threshold distance. This creates an effect that the particles will form clusters of different sizes that can be size of 2, 3, 4, or more, as it can be seen in this video. The last exercise, you're going to apply this equation, and then you're going to try to create similar behavior that is found in this video. These were all of the exercises that we covered during our lecture, and now you will see some problems in the next slides that you will work on during the study hours. And if you have any questions, I will be here on Zoom to help you, and you can always ask me if you need help. Thank you very much for listening.